Welcome back to the deep dive. As we push towards a future powered by renewables, one word keeps coming up: flexibility. The grid needs it.
Absolutely. Without it, solar and wind just, well, they aren't enough on their own.
Exactly. And flexibility really means storage, finding big, affordable ways to keep the lights on when the sun's down or the wind drops.
Mm-hmm.
So today, we're focusing on a real heavyweight in storage, one of the oldest, actually: pumped hydro energy storage, or PHES.
Right, the original grid battery, in a sense.
Pretty much. But we're not just looking back. We're doing a deep dive into one specific piece of research that honestly changes how we should think about PHES potential. It's called Revisiting the Potential of Pumped Hydro Energy Storage, a method to detect economically attractive sites.
That's a really interesting one.
It is, because it connects the dots.
Yeah.
It takes Geographic Information Systems, GIS, to find the actual spots on a map.
The physical locations, yeah.
Then it layers on detailed cost estimates for those specific sites, not just averages. And the final step, it feeds those costs into energy planning tools to see what gets built in the future.
It's that end-to-end approach that's quite novel, linking the geography directly to the economics and then the system planning.
Exactly.
And it's timely, too, considering the storage race that's going on. I mean, PHES used to be basically everything, right? Over 97% of global storage capacity until maybe 2017.
Yeah, dominant for decades.
But lithium-ion, Li-ion, has just exploded onto the scene. Projections show it could actually overtake PHES globally in total capacity by, 2028?
That's incredibly fast, a huge shift. So
Yeah.
why spend all this effort revisiting pumped hydro if batteries seem like they're winning the race?
Well, that's sort of the core hypothesis of this study, isn't it? They're betting that PHES, done right, will still be cost-effective, maybe not the absolute cheapest in every case, but definitely comparable, or second cheapest, even against really optimistic future projections for utility-scale Li-ion.
Okay, so it's a cost competition thing.
It's partly cost, but it's also about diversification,
Right.
a hedge. What if we run into bottlenecks with lithium or cobalt for all those batteries?
Supply chain constraints.
Right, exactly. PHES doesn't have those same material issues, so it's potentially this very reliable large-scale alternative. Maybe Plan B, maybe even Plan A in some places.
Okay, let's unpack the method then. You mentioned batteries can go almost anywhere, but PHES needs specific geography, elevation, water. How did this study get more precise than just looking at mountains on a map?
Right, that was the key. They moved beyond those course estimates by focusing only on site-specific potential. And crucially, they limited their search to 4 specific designs or topologies.
4 types. Why only 4?
They picked the ones they figured had the best shot at low costs and high energy potential, and ones where water availability was explicitly considered. That water part is critical.
Okay, walk us through those 4 designs.
Sure. First is the existing pair. Pretty straightforward. Find 2 existing reservoirs, could be lakes, dams, whatever, that are reasonably close, say within 20 kilometers.
Okay.
But have a good vertical drop between them. They set a minimum head, that's the term for the elevation difference, of 150 meters.
Right. Head being that vertical distance the water falls. More head means more power potential general.
Exactly. More pressure, more energy generated when the water flows back down. Higher head usually means smaller, cheaper reservoirs for the same power output.
Got it. What's topology number 2?
Second was one reservoir. In this case, you find an existing lower water body, a lake, a river maybe, and you model building a new upper reservoir to pair with it.
Okay, so half existing, half new construction.
Right. Then the third, which is pretty clever, seawater. Build an upper reservoir near the coast and use the sea itself as the lower reservoir.
Infinite lower reservoir, basically.
Mm-hmm.
Sounds smart, especially for places with long coastlines.
It is potentially huge capacity, but as we'll see, it comes with its own engineering challenges and costs.
Okay. And the last one?
Number 4 was the river topology. Build an upper reservoir, but use a nearby river as the lower water source. And importantly, they filtered out rivers that aren't perennial, meaning they don't flow year-round.
That seems like a really practical filter. You need water all the time for this to work reliably.
Absolutely. And they didn't stop there with filtering. They also screened out sites that were too close to sensitive areas.
Like national parks or towns.
Exactly. World Heritage sites, protected zones, inhabited areas, even major roads or railways. They put buffer zones around those, like 500 meters or 200 meters, depending on the feature.
So avoiding places where it would be difficult or impossible to get permits or just too expensive.
That's the idea. Make the potential sites more realistic from the start.
So remind us again, why is this focus on water and these filters Such a big deal compared to older studies.
It's the crucial difference. So many previous large-scale studies just looked at topography. Where are the hills?
Yeah.
This study insisted on confirming a viable water source for each topology and respecting those land use constraints.
Hmm.
That makes their final numbers much more conservative, yes, but also much more grounded in reality. A site without water or that's in a national park isn't a real project.
And they tested this whole GIS approach in the South Andes.
Mm.
Chile, Peru, Bolivia.
Yeah, a perfect testing ground. You've got Chile's massive coastline for the seawater type,
Uh-huh.
Peru's complex river systems, and then landlocked Bolivia relying entirely on internal rivers and lakes.
Give you a bit of everything.
Exactly. A really good comparison across the different topologies and geographies.
Okay, so they run this sophisticated GIS analysis, apply all the filters.
Hmm.
What did they actually find? What's the technical potential in those three countries?
Well, they flagged 472 promising projects in total, and the scale is, frankly, enormous. The total energy capacity they detected, assuming a standard 12-hour storage duration, came out to almost 20 terawatt hours.
20 TW8. That's a lot of energy.
It is 19,900 gigawatt hours, to be precise, and the associated power capacity was 1,657 megawatts.
Wow. Okay, put 20 TWH into context for us. How does that compare to, say, the daily electricity use in those countries?
It completely dwarfs it. The total potential found across the three countries is more than 20 times their combined average daily electricity load.
20 times?
Yeah. Take Chile, for example. They found 9.9 TW of potential. Chile's daily load is around 360 GWH, so that's, what, 27 times the daily need?
Okay, so this isn't just about shaving peaks. This is potentially multi-day, even multi-week energy storage, enough to ride out lulls in wind and sun.
That's exactly the implication. It suggests the kind of deep storage capacity needed for a grid running entirely or almost entirely on renewables, real system resilience.
Where did most of that 20 TWH come from, topology-wise?
The biggest chunk, maybe unsurprisingly given Chile's geography, was seawater, contributing 8.5 TWH.
Right.
After that, one reservoir sites added up to 6.0 TWH, and river sites accounted for 5.2 TWH.
And the existing pairs.
Yeah.
One's using two current reservoirs.
A much smaller slice, only about 0.1 TWH. But, those might be some of the lowest hanging fruit in terms of cost and permitting, even if the total capacity isn't huge.
Interesting. And how did the potential break down by country? Did the water constraints really shape that?
Definitely. Chile, with its coast, had the most total potential. 9.9 TWH, mostly from seawater, as you'd expect.
Uh-huh.
Peru came in next with 7.5 TWH, but theirs was dominated by river potential.
Okay.
And Bolivia, being landlocked, found 2.5 TWH entirely from river and one reservoir projects. No seawater potential there, obviously.
So the model reflects the geography and the water reality. Now, you said earlier studies sometimes threw around much bigger numbers. How does this 20 TWH compare?
Yeah, this is where the methodology really shows its value. Some older, purely topographical studies for South America suggested potentials over 1,000 TWH, maybe even higher.
1,000 compared to 20. That's a massive difference.
It is, but it's not that the study failed. It's that it succeeded in being realistic. By adding the water requirement and the land use filters, they cut away the theoretical potential that wasn't actually buildable. That drop from 1,000 down towards 20 is actually a sign of more precision, not less potential overall. It gives you sites you could actually develop.
Okay, that makes sense. It's filtering down to the viable projects. Which brings us to the economics. Finding a spot is one thing, but does it make financial sense? Especially against falling battery costs?
Exactly. This is where it gets really critical. The researchers didn't just find the sites, they calculated the costs for every single one of those 472 projects.
And not just a rough estimate.
No, quite detailed. They included estimates for building the reservoirs, the pipes, the penstocks, the turbines and generators, access roads, and crucially, the transmission lines needed to connect the site to the grid.
Right. Connecting it is a big cost factor.
It can be, yeah. So with all that, they could build these cost potential curves. Basically, plotting the investment cost, they used euros per kilowatt hour against the cumulative energy capacity you get at or below that cost.
And what did those curves show immediately?
Well, the first takeaway was that a lot of the PHES potential they found is already significantly cheaper than what Li-ion battery systems cost today.
Okay, cheaper than current batteries.
Yeah.
But the real test is future batteries, right? Everyone expects Li-ion costs to keep plummeting.
Correct. So they compared against projections. Optimistic ones for utility-scale Lion systems, maybe with 4 hours of storage, suggest costs might hit around €130 per kilowatt-hour sometime shortly after 2030.
So 130 kilowatts is the benchmark to beat in the nearish future.
Kind of, yeah. And what the study found was huge capacities below that level. Chile had 9.0 TWH, Bolivia 2.5 TWH, and Peru 7.0 THS projects cheaper than that 130 mark.
Wow. So a massive amount of PHES is potentially competitive even with post-2030 battery prices.
Then it gets better. They found really significant chunks cheaper than even 50 euros per kilowatt hour.
50 euros? That sounds incredibly cheap for storage.
It is. We're talking 3 TWH in Chile, 2 TWH in Bolivia, and 4 TWH in Peru, below that 50 kilowatt threshold. And that figure, 50 kilowatt hour, is lower than even the most aggressive, optimistic cost projections for Lion systems way out in 2050.
Okay, so this strongly confirms their initial hypothesis. PHES isn't just a backup plan. For the right sites, it looks like it could be fundamentally cheaper than batteries for large-scale storage, even long-term.
That's what the numbers suggest, especially when you factor in that PHES plants can last 50, 80, maybe even 100 years, while batteries need replacing much sooner. That long lifespan really helps the overall economics, the levelized cost.
But were all the PHES types equally cheap? Did those 50 kilowatt sites come from everywhere?
No. There was a definite split. The real cost champions were the river and one reservoir topologies. That's where most of that ultra-cheap potential under 50 kilowatters came from.
Okay, so river-based and building one new reservoir seem to be the sweet spots. What about seawater?
Seawater potential starts at higher costs. The cheapest seawater sites they found were around 120 kilowatters.
So already close to that projected 2030 Lion cost. Why are they more expensive? Is it the saltwater issue?
Exactly. You need corrosion-resistant materials for everything the water touches. Pipes, turbines, that adds cost. You also have to be very careful sealing the Uppy reservoir to stop saltwater leaking into the groundwater.
Right, environmental protection.
Yeah, and often these coastal sites might be more remote, needing longer, more expensive transmission lines to connect to the grid.
So while seawater offers huge technical potential, its economic competitiveness against future batteries might be more limited, maybe fading in the 2030s.
That's a possibility, yes. It might become less competitive if battery costs fall as fast as some hope, though it still provides a massive amount of capacity if needed.
Okay, so we have these detailed site maps and cost curves. How does actually using this detailed information change how we plan the future grid?
Right, that was the final piece of the puzzle. They took their findings, specifically for Chile, and fed them into an energy system optimization model called LILO.
LILO. And what does that tool do?
It basically designs the cheapest possible power system for a future scenario. In this case, they looked at Chile in 2050, aiming for a fully renewable system. LILO figures out the optimal mix of generation solar, wind, etc., transmission lines, and storage, including PHES, batteries, hydrogen, whatever minimizes the total system cost.
So it makes the investment decisions based on the costs you feed it. What happens if you just give it a single average cost for all PHES, like planners often do?
That was the key comparison. When they ran LILO using just one generic average cost for PHES, they called this the base case. The model significantly underestimated how much PHES it should build.
Underestimated.
By how much?
By 50%,
Yeah.
compared to a scenario where they simply used different average costs for each of the 4 PHES topologies.
Wait, just separating the costs by type doubled the recommended PHES deployment? Pretty much, yeah. Because that generic average hides the existence of those really cheap river and one reservoir sites, the model couldn't see them properly.
Okay, that's huge.
And then they went even more detailed, using 3 different cost levels within each topology. That increased the optimal PHES size again, and it really changed the mix. Suddenly, those super cost-effective river sites got picked up by the model, making up about a third of the total PHES capacity it recommended.
Whereas they were ignored when using the average costs.
Largely, yes. It shows that the granularity matters enormously. If you don't tell the planning model about the cheap options, it won't choose them.
The real-world impact is obvious. Using averages could lead planners to underinvest in PHES, potentially choosing more expensive options instead.
Absolutely. Putting it all together using these detailed, site-specific cost curves from this study resulted in the LILO model recommending 5 times more PHES capacity for Chile in 2050 compared to a previous study that used generic costs from literature.
5.
And 1.6 times more than if they'd just used their own single average cost. That detail is a massive multiplier for PHES deployment in planning.
And in that optimized 2050 system for Chile, with all this cheap PHES included, what happened to the competing storage technologies, like Li-ion batteries?
They played a surprisingly small role in the model's final recommendation. Depending on the specific scenario details, Lion only accounted for about 2 to 40 gigajoule of storage.
That's tiny compared to the TWZOS of PHES potential.
It is. It suggests that, at least in geographies with good PHES potential like Chile, PHES, possibly alongside hydrogen for very long duration needs, could handle the bulk of the storage job cost effectively.
Which could mean maybe we don't need quite as many grid-scale batteries as some forecasts suggest. That manufacturing capacity could go to electric vehicles instead.
That's a potential implication, yes. That PHES could free up battery supply chains for other crucial decarbonization sectors, like transport.
Okay, so let's wrap this up. What are the key takeaways for you, the listener, from this deep dive?
I think there are a few big ones. First, the sheer scale of PHES potential, even with strict, realistic filters, is immense in regions like the Andes, potentially over 20 times the daily electricity demand.
Just huge potential.
Second, and maybe most critically, PHES, especially those river and one reservoir types, look set to remain highly cost competitive, even against very cheap future batteries. The study's main hypothesis seems well supported.
So it's not just an old technology, it's a future-proof one in the right locations.
Seems like it. And the third point is really methodological, but it has huge practical consequences. Using detailed site-specific data matters. Water availability checks, realistic land use, and granular cost curves are essential for energy planning. Using symbol averages will likely lead you to underestimate PHES.
Don't rely on the averages. The details unlock the real potential.
Exactly. Which naturally leads to the question, what's next? Where does the research need to go?
What did the study recommend?
They highlighted the need for more detailed work on the river-based systems, specifically verifying actual water flow rates year-round, not just mapping the river.
Right, confirming the water is really there when you need it.
And also doing more detailed studies on potential ecological impacts and ensuring compatibility with existing water uses. Refining those river estimates seems key.
Makes sense. And before we finish, you mentioned a provocative thought for our listeners.
Yeah, just something to mull over. This study found almost 20 TWNOBUAs of technically feasible, cost-analyzed PHES potential in just these 3 countries. A massive amount.
Right.
Yet when the optimization model designed the most cost-effective renewable grid for Chile in 2050, it only ended up selecting projects that amounted to about 5% of that total available PHES potential found in the country.
Only 5%. So
Yeah.
even though we need massive storage for the transition?
The actual physical potential available, at least in regions like this, might be vastly larger than what we ultimately need to build to get the job done cost-effectively. The resource base is just staggering.
That really puts the scale of the challenge and the opportunity into perspective. We have the tools, geographically speaking.
We seem to have a lot of them, yes.
This has been a fascinating deep dive into revisiting the potential of pumped hydro energy storage, a method to detect economically attractive sites. Thanks for walking us through it.
My pleasure.
And thank you for joining us.